After studying this module, you shall be able to know about factors which affect the stability of a complex, learn about the electron receptor properties of metals, study the nature of ligands related to metal-ligand stability. Introduction. We have already discussed the stability constant in the previous modules. In this module, let us discuss the factors that affect the stability of the complexes. As we know that the stability constant of a complex is the equilibrium constant for the complex ion formation. Stability of a complex refers to the tendency to exist under equilibrium conditions. It is directly related to metal-ligand bond energies. Generally, the complexes are not prepared from their components in gaseous phase, but these are prepared in aqueous solution, and there are number of factors which affect the stability of complexes. Factors affecting the stability of complexes. The following are the factors which determines the stability of complexes. Nature of the central metal ion. Variation in the stability for a series of complexes of metal ions with a common set of ligands depends on the charge on metal cation. Generally, the metal cation in higher oxidation state form more stable complexes than that of in lower oxidation states with a given ligand like halides or ammonia or water. However, there are few exceptions with ligands such as carbonyl, trimethylphosphine, bipyridyl, cyanide, which form more stable complexes with metals in lower oxidation state. These ligands have vacant pi star antibonding molecular orbitals for accommodation of lone pairs of electrons donated by metal atom or cation and hence form pi back bonding. The electron-rich cyanide is not only a poor pi acceptor but is also a good sigma donor and therefore forms complexes with metal atoms in higher oxidation state. Size of central metal cation. For a given ligand and metal of same oxidation states, stability of complexes increases with decrease in size of metal cations. For M2 plus ions, the general trend in stability for complexes is barium, strontium, calcium, magnesium, manganese, ferrous, cobalt, nickel, copper and zinc. Trend in stability is known as Irving-Williams series. This order of stability is consistent with charge to radius ratio concept because the radii decrease from barium to copper and then increase to zinc. The order of size of dipositive ions is barium, strontium, calcium, magnesium, manganese, ferrous, cobalt, nickel, copper, but zinc is greater than copper. Since size of zinc is larger than that of copper ion, therefore stability of Zn2 plus complex is lower than that of copper 2 plus ion. The graph shown in figure is a plot of log K of complexes of M2 plus ions with oxalate ions. The log Kf values of barium, strontium, calcium, magnesium, manganese and zinc complexes lies on a line because there is no additional CFSE. Though copper 2 plus complexes have an additional Eg antibonding electrons, they are more stable than nickel 2 complexes. This is due to the John-Teller distortion. During the distortion, 2 electrons are lowered in energy while only 1 electron in dx square minus y square orbital is raised by an equal amount in energy as compared to the octahedral field. It results in strong bonding of 4 ligands in xy plane of tetragonally distorted copper 2 complex and increase the value of formation constant. The axial position are weakly bound, which is responsible for higher lability of complex. You can see the graph which shows the variation of formation constant for M2 plus ions of Irving-Williams series. The value of stability constant for octahedral complexes of manganese to copper 2 plus ion increases more rapidly because these ions are additionally stabilized by CFSCs in octahedral fields. The stability of octahedral complexes of Zn2 plus is lower than of copper 2 plus ion because its CFSC is 0 and it lies on the line representing the stability of barium, strontium, calcium, magnesium and manganese ions where CFSC is also 0. Electron acceptor property of metals. Arland et al. In 1958 has classified the metals into three categories on the basis of their electron acceptor properties. Highly electropositive metal ions. Metal ions having high electropositive character, small size, high oxidation states and no easily distorted outer electrons. These metal ions form their most stable complex with ligands favoring electrostatic bonding. They have more stable complexes with the first elements of group 15, 16 and 17. They include smaller ions from the alkali metals, alkaline earth metals and lighter transition metals in high oxidation states. They are also called hard acids or hard metals. It includes the following ions. Some of them are hydrogen, lithium, sodium, potassium, beryllium, magnesium, calcium and so on. The order of stability of complexes of these metals with ligands having the following donor atom are as follows. Fluoride greater than chloride, greater than bromide, greater than iodide. Oxygen is much greater than sulfur, which is greater than selenium, which is greater than beryllium. Nitrogen is again much greater than phosphorus, which is greater than arsenic, which is greater than antimony. Less electropositive metal ions. Metals are less electropositive, have relatively full d orbitals and form their most stable complexes with ligands which in addition possess lone pairs of electron, have empty pi orbital available to accommodate electron pairs from d orbitals of the metal. They form stable complexes with ligands which have donor atoms from subsequent periods. The metal-ligand bond in these complexes is covalent. The order of stability is the reverse of metals which are highly electropositive. The increase in availability of empty d orbital in heavier elements favors an increase in stability of the complexes. They are also called soft acids or soft metals. The order of stability of complexes with the ligands having following donor atom is as follows. Fluoride less than chloride less than bromide, which is less than iodide. Oxygen much less than sulfur less than selenium, which is less than beryllium. Nitrogen is much less than phosphorus less than arsenic, which is less than antimony. Furthermore, they form stable complexes with carbonyl, O-phenanthroline, olefins because these have vacant pi orbitals of low line energy. It includes ions, copper, silver, gold and so on. Borderline metals. Borderline metals include dipositive metal ions of 3D series which are manganese, ferrous, cobalt, nickel, copper, zinc. For a given ligand, order of stability of complexes is as follows. Nature of ligands. Basic character of ligands. In general, more is the basic character of ligand, more easily it can donate its lone pair of electron to the central metal ion. Hence, greater is the stability of the complex form. For example, for a given dipositive M2 plus of 3D series transition metal ion, order of stability of complex with ammonia, water and fluoride is ammonia is greater than water, which is greater than fluoride. Covalent character. Higher the covalent character, higher will be the stability of the complex. For example, Order of stability and covalent character of complexes of silver with halogen is silver iodide, silver bromide, silver chloride and silver fluoride. Pi bonding capacity of ligands. The ligands like carbonyl, cyanide, alkenes, phenanthroline, bipyridyl, trialkyl phosphine and alkyl sulfur, etc. have vacant pi or d orbital to form pi bond and hence stable complexes with metals. Dipole moments of ligands. For neutral ligands, higher the magnitude of dipole moments, higher will be the stability of the complex. For example, the order of stability of complexes of ligand having nitrogen as a donor atom is ammonia greater than ethylamine greater than diethylamine, which is greater than triethylamine. The chelate effect. The polydentate ligands have geometries such that they can form more than one coordinate bond to the same metal cation. Such ligands are called chelating ligands. These ligands generally are non-linear. The complex formed by the coordination of a polydentate ligand to a metal cation is called chelate complex or a chelate. Chelating ligand form a stable complex than the analogous monodentate ligand. It means that chelated complexes are more stable than their non-chelated analogues. This effect is called as chelate effect. Let us consider an example of complexes, that is complexes from hydrated cadmium ion with methylamine, ethylene diamine and triethylene tetraamine ligands, where methylamine is monodentate, ethylene diamine is bidentate and triethylene tetraamine is tetradentate ligand. The structure of cadmium complexes with all these three ligands are shown. Cadmium methylamine is a non-chelated complex, whereas cadmium ethylene diamine and cadmium triethylene tetraamine are chelated complex ions. Therefore, the order of stability is given as follows. The above order of stability can be explained as methylamine, ethylene diamine and triethylene tetraamine ligands are competing for the formation of complexes with cadmium 2+ ion in aqueous solution. The probability of either of them coordinating to the first site may be taken as equal. Once one end of ethylene diamine and triethylene tetraamine is attached to cadmium 2+ ion, it is seen that the second amino group of ethylene and triethylene tetraamine is now greater in vicinity of cadmium 2+ ion than the second methylamine ligand, which is free to move randomly in the solution. Thus, probability of second amine group of ethylene diamine or triethylene tetraamine to attach to cadmium 2+ ion is greater than that of monodentate ligand methylamine. This indicates that formation constant is larger for the formation of chelates. Also, the chelates in which one ligand form two or more rings are more stable than the complex in which one ligand form only one ring or no ring. The dependence of stability of chelate on the size of chelate ring is shown in this figure. In general, the chelates having 5-membered rings are more stable than 6-membered rings, are in turn more stable than the 7-membered rings. Thus, the chelate effects weaken as the ring size increases. Smaller rings generally involve excessive strain and become less stable. When the chains and rings become much larger, the enhancement of local concentration decreases and the resulting complex becomes less stable. Macrocyclic effect. Macrocyclic ligands are large ring size compounds even without a metal atom present, and these ligands have several donor atoms inside their rings to form coordinate bonds with the metal ions. Chlorophyll, heme and vitamin B12 all contain tetradentate macrocyclic ligands. As stated earlier, the chelating ligand form more stable complexes than analogous monodentate ligand, and the macrocyclic ligands of appropriate size form more stable complexes than chelating ligands. There is a competition between a non-cyclic ligand and a macrocyclic ligand having the same type of donor atoms, and the complex formed by macrocyclic ligand will be more stable. This effect is called macrocyclic effect. Resonance effect. Resonance enhances the stability of complexes. For example, acetyl-acetone anion ligand shows resonance and form a chelated complex. As a result of resonance, the MO bonds are equal in length and strength. Steric effect or steric hindrance. If a bulky group is either attached to a donor atom or to the atom adjacent to donor atom, the metal-ligand bond becomes weak and the stability of the complex decreases. This effect is called steric effect. For example, ethylene diamine and N-tetramethyl diethylene amine both are bidentate ligands and form chelates with nickel 2+ ion. The complex 2 is less stable than 1 because in complex 2, the methyl group attached to donor atoms create steric hindrance and decrease the stability of the complex. Geometrical factors. The stepwise formation constant Kn, where n varies as 1, 2, 3 and so on in a series, decreases as the value of n increases. But it is not true if the geometry of all the complexes are not same for all the members of the series. For example, the formation of diamine silver complex in aqueous solution is given by this equation. In this case, the order of stability constant will be K2 greater than K1 because the silver ion is get hydrated and exists as AgH2O4 complex. Therefore, the first step will be substitution reaction in which ammonia acts as a nucleophile and one water molecule is left, results in the tetrahedral substitution product. In the second step, the aqua ligands are lost and form NH3AgNH3, which is linear in shape. Another example is the formation of cobalt chloride from cobalt aqua complex, in which the change in geometry takes place from octahedral to tetrahedral. Let us summarize. The metal cation in higher oxidation states form more stable complexes than that of in lower oxidation states with a given ligand such as halide, ammonia or water with some exceptions. Stability of the complexes increases with decrease in size of metal cations. Metal having high electropositive character, small size, high oxidation states form more stable complexes with ligands favoring electrostatic bonding. Metals with relatively fully d orbitals form their more stable complexes with ligands having lone pair of electrons and pi orbitals available to accommodate the electron pair from d orbital of the metal. Nature of the ligands like basic character, covalent character, dipole moment and pi bonding capacity are also important factors that should be taken into consideration. Other factors like geometrical, macrocyclic, chelate and resonance effects regarding the stability of complexes has discussed in detail.